So continuing on under the WASIS, topic of thermal properties of matter. We have looked at the phase diagram of water and carbon dioxide, and we have looked at some concepts, fusion, triple point of water, sublimation, and the like. So let's just look at some examples that will just help us cement what we have looked at so far under melting, under the concept of melting or crystallization, right? Or freezing and melting, the concept of freezing and melting. So we have a question here to say, how much heat is released from a 500 gram of water as it, all right? So we're looking at just this question. Is asking us how much heat is released from 50 gram of water as it changes from liquid to crystalline phase at 0 degrees. How much heat is released? All right, we say that if you are coming from liquid to solid, heat is what? Heat is lost. We lose heat. In that way, heat is lost. But if we are coming from solid to liquid, heat is gained. All right, like that. So that's why we're even seeing here, they are asking us to say how much energy is released, all right, more like lost from a 50 gram of water as it changes from liquid to crystal. Crystalline phase is the solid phase at 0 degrees, all right? And also we have been asked another question to say from steam to water at 100 degrees. So how much heat is released? All right, there's this word released or lost. So on question 1, on part 1, here we have the formula. Heat is equals to mass times the heat of fusion. Why are we using heat of fusion? Because fusion is dealing with melting, all right? The idea of melting or crystallizing, all right? Or crystallizing. Crystallizing is the opposite of melting. It's more like solidifying. Most of you guys know it by the word solidifying. Solidifying or melting. So whenever we talk about melting, crystallizing, here they have used the word crystalline, going from liquid to crystalline. If it is going from liquid to crystalline, it is what we call freezing. It's freezing. So we look at the heat of fusion. It is usually given, and in this case, the heat of fusion is given as 334 joules per gram. This is the heat of fusion. All right, so we are using per gram, so we don't need to change. If we are using per gram, then we don't need to change this from gram to kg, the mass given. But if it was per kg, we would have changed this from grams to kg. So heat of fusion is usually given. So to compute the heat which will be released, we just multiply the 50 gram, multiply by the heat of fusion, we have the heat which will be released when water freezes. All right, when water freezes, there will be heat which is released. But when water melts, it will gain heat. I hope you get the difference. Freezing, when it freezes, heat will be released. But when it is melting, heat will be absorbed. All right. So here we have another question which is saying, I hope we are clear on part 1. Are we clear on how to compute part 1?
Yes, sir.
Yes, sir.
Okay. So we go to part 2. Part 2 is talking about changing from liquid. Part 2 is talking about steam, okay, coming from steam to water. So what is that process called? From steam to water? Anyone who knows? What is the process which takes place if we are having steam changing to water? What is it called?
Condensation.
I was going to be surprised that you guys were taking time to answer this one. So it's going to condense, all right? So meaning the heat of vaporization will be lost. Some heat, which was the reverse of evaporation, will take place, all right? So from steam to water at 100 degrees, we use the formula, all right? We use the formula of Q, all right, is equals to M times the heat of vaporization, all right? Heat of vaporization is there for, it applies for evaporating and condensing substances. So the heat of evaporation, which is this, for water is given as this, 230, all right? This is given per gram. So we'll not change the water which was given in grams into kg. So we'll compute it like that. So we'll get the energy that is required by just multiplying mass times the heat of vaporization like that. So this is a situation whereby we just have an isolated system. Water changing into steam changing into water. We also saw here liquid changing into ice, into crystalline. But what we'll see under calorimetry is we'll see a lot of things happening. We'll see different substances interacting. You have liquid here. Maybe you have a glass like this. And then you want to drink some juice. All right. Then you get some ice. You drop into that. You drop into the glass, and then you fill it up with some juice like that. So that what do we do so that we can cool this juice, all right? And what will happen, the process that will happen is what we call calorimetry. We'll see that the ice will start melting. As it will start melting, it will cause the temperature of the system to change. Finally, the temperature of the system will change. So we'll look at that later on under this same topic that we're looking at, calorimetry. So when we look at calorimetry, okay, a calorimeter is a device, all right? So this word calorimetry comes from the word calorimeter. So the calorimeter is just a device that helps us to, study how temperature changes as different substances at different temperatures interact. Like we are saying, if we have ice, right, ice blocks and water, if we place them in a calorimeter, how are they going to interact? So the study of that is called calorimetry. All right, a calorimeter is a heat insulated device. It makes sure that no heat can come in and no heat can go out. So even if here we are not talking about a situation where we put water on a stove, here we are talking about isolated. There's no heat coming in, there's no heat coming out. They are just substances interacting inside there. And the equation actually that we work with under the concept of calorimetry is heat lost will be equal to heat gained. So change in heat at the end of the day is equals to 0. All right, because heat lost is equals to heat gained. All right, at the end of the day, change in heat is equals to 0. or when we sum the heat that has been gained and the heat that has been lost, we see that it gives us 0 because we are not adding heat. We are not getting a torch or a brazier and putting a container on it to study calorimetry. Calorimetry, we study it when the system is isolated, such that internally things can just happen. Heat can be lost and heat can be gained. All right. So all these concepts that we have been looking at talk about boiling, talk about melting, talk about, just substances changing the temperature, the formulas that have been looked at. All of them will now come and summarize them under the topic of calorimetry. So I hope you guys have been paying attention to what we have been looking at. And nevertheless, I'm just going to run through a quick summary of what we have looked at. And then from there, we can put the concept of calorimetry into perspective. Is that okay?
Yes, sir.
Okay. So first of all, we looked at just the concept of changing temperature, right? If you remember. So we said when a substance of mass M is heated, so we have this word, it is when it is heated or it's cooled through a temperature interval, all right? If the temperature changes, it will gain energy or it will lose some energy, all right? And this is what we faced when we looked at this topic. We looked at this formula, all right? We say that energy is equals to mass times this C. Anyone who remembers that what this word C means stands for? C. This C which is here. Anyone who remembers what it stands for?
Specific heat capacity for the substance whose temperature is changing.
Awesome, awesome. So we say that for a substance whose temperature is changing, it will have a specific heat capacity. That is the first thing we looked at. So we'll have the final temperature minus the original temperature happening this way. So heat can either be lost or can be gained. So remember this concept. We are going to apply it in calorimetry. And also, we also looked at, fusion, just like the one that we are looking at. We are just from looking at, all right? When a substance of mass M melts, all right, to melt is to turn from liquid, all right, to turn from solid to liquid, right? That's melting, solid to liquid. But also in the bracket, we have put crystallize. Crystallize is the opposite of melting. Crystallize is to freeze, all right? So we are saying when a substance of mass M melts, or when it crystallizes, or when it freezes, heat can either be gained or it can be done what? It can be lost, all right? That amount of heat which is gained or lost when a substance is changing state from either solid to liquid or from liquid to solid is given by this expression. All right. Now the plus and minus you see here is we are saying heat can either be gained or lost in the process. All right. That's why we have plus or minus. So if it is melting, we'll have a plus. If it is freezing, we'll have a minus. All right. But when you are doing your computation, we'll see what will happen, whether we should put a plus or minus. All right. But sometimes we just leave it like that. The sign appears on its own when we do the computation, because sometimes we don't even know what will happen. We just write equations. So in our equations, we usually don't even put this plus or minus. We just write the equation as Q is equals to M H F. All right. Anyone who knows what this HF stands for? HF, what does it stand for?
Heat of fusion.
Awesome. Awesome. All right. Good. So we have HF given as heat of fusion. All right. And when heat of fusion is being absorbed, all right, if we apply sufficient energy, all right, to a solid, we apply sufficient energy, we are going to change its state to liquid. Under this process, phase changes. But when the temperature is changing, here phase, under this process, no phase change takes place. When temperature, at the moment when temperature is changing, we don't expect phase to change. But when we have heat of fusion like this, we expect the phase to change. What do we mean phase? We mean it will turn from solid to liquid, or vice versa. It will turn from liquid to solid. Here phase changes, all right? And when we come to the last one, here, when a substance of mass M vaporizes, so it can either vaporize or condense, all right? It gains or loses an amount of energy Q, so given by this. So plus or minus, again, we have said is losing or gaining. And here a phase changes. So it can either turn from solid or from liquid, right? It can either turn from liquid to gas, or from gas to liquid when condensing. So when condensing is taking place, here we lose. Here we lose energy. We lose. And when evaporation is taking place, here we gain. We gain energy. The substance gains energy. So this is the equation. And what does this HV stand for?
Heat of vaporization.
Okay. Heat of evaporation, or heat of evaporation, or heat of evaporation. It's usually the same thing. So here we expect phase to change. All right, phase change takes place. So just to cement what we have looked at, let's look at the diagram. All right. So this diagram tells us just how different, how a substance changes state or changes its temperature, like that. So heat associated with temperature rise and change of phase of a substance. So here we are looking at the heat associated with temperature rise or phase, change of phase of a substance. All right. So if a substance is in solid state, what will happen is its temperature will continue doing what? Increasing. When we add what? When we add heat. So here we are adding heat. Here temperature is changing. And here we use this formula. All right. Energy times mass times the specific heat capacity times the change in temperature. When, for example, if it is in solid state, there's no phase changing, it is still a solid, temperature will rise, all right, until a point where it will start melting. When we go to a point where we have reached at a temperature at its melting point, temperature will remain constant. There will be no change in temperature, but we'll continue adding heat. we are continuing to add heat. And here heat will be absorbed in form of fusion, which will change the state from solid. So this is where solid now is changing to liquid. So we have solid. In fact, in this state, we have a mixture of solid plus liquid in this state. Here we only have solid, but when the temperature remains constant for fusion to take place, for melting to take place, some solid will start melting. So what was solid will start turning into liquid. Temperature will be the same until all the solid turns to liquid. After all the solid has turned to liquid, then the temperature starts to increase. Under liquid, all the solid has turned into liquid, temperature starts to increase. All right. So as the temperature increases, there will be no phase change. It will be all liquid, no solid, no gas, just liquid. But at a temperature when it starts evaporating, all right, here, remember we use this formula again. Mass is equals to mc delta T. So you should know which formula to use at what point. Is temperature changing or it's remaining constant, or what is happening? Do we have this or that? Or do we have a situation where we will first have heat absorbed, then phase will change? From there, after phase changes, temperature starts increasing. What is happening here? Now, this is the diagram that guides us. We know we should be able to know at what point and what formula to use. So, when we reach at a point where we have reached the melting temperature of substance, I mean, not the melting, but the evaporating temperature, the temperature will remain constant. In this period, we'll have liquid turning to gas. And actually what happens is we'll have a mixture of liquid and gas. All right, until all the liquid has turned into gas, that's when temperature can change. So if you find water boiling, all right, if you find water boiling, you put a thermometer there in the boiling water. You leave it for 2-3 hours. You'll find the temperature is constant. Sometimes you find it at 98, 99, or 100. Try that. Use your finger as a thermometer. You know, a finger can also detect temperature change. Not so. So when water is boiling, you put a finger there and then try and find out if you feel any change in temperature until all the water has finished boiling, has evaporated. Can you do that as an experiment?
Oh.
Sorry?
No. We can't.
No, for the sake of science, you have to try, because I don't know, if you have a thermometer, then you do so. But for the sake of science, get your finger, put in the boiling water, and then just try and measure. If once it is boiling, if you feel any temperature change, or it is becoming hotter or colder, you tell me. Is that okay?
No, sir, it's not.
You guys are not scientists. You guys, you should take risk for science's sake. All right. Oh, Mr. Gilbert texted and said, oh no, you should try out these things. Anyway, in fact, if we end here, this is the most important thing. If you guys get to just understand what has happened, and know when to use which formula and whatnot, then you guys are warm and dry. All right. So this is probably where we are going to end our other phase of lecture. God willing, I hope to arrange another class, hopefully during the week. I can't promise that Monday or Tuesday, because I don't know how my week will go, where we can just conclude this topic by some questions, because mostly we've been looking at just concept after concept after concept. So we'll probably solve the tutorial sheet under this topic. Then we look at some concepts here, because even as I was going through the notes that they give, I know those notes, studying them on your own like that, I know they are challenging because they need explanation. They need someone to explain. So I hope the explanation I've given is helpful, and that you will find it easy in your exams to if a question is given on this topic, to answer. And yeah, so I guess that's it for today, unless we have any question. Any question? Okay. Do you have a question? If we don't, then we can call it a day. Have a wonderful day. And
A question, sir.
okay, you can ask.
Yeah. Now, what if we put, for example, there are three substances, two substances, and then you have another one which is different, and then one is water, but water is maybe in two forms. Another one is ice, and then another one is water at normal temperature. Put in calorific, and then this other substance, of course, is for example, water is steam. Yeah, water is a steam. This other substance is a solid, and it turns out it becomes liquid. All of them become liquid at the end of it. Now the issue of change there, the heat gain, I don't know how we can arrange it, like that formula for that one which involves specific heat capacity of specific heat capacity, and also that formula of heat fusion, or specific heat fusion or vaporization. I don't know whether we can say no, the heat gained by this is equal to the heat. I don't know how that can be done.
Yes. In fact, that is why I'm saying the next time we'll look at our questions, and then we'll look at questions like that. So anyway, for the sake of that question that you have asked, so let's assume we have a cup like that. It has ice. It has also liquid water. And then let us assume it has, what other substance is that? Let us also assume, let's look at two instances. We have, in fact, let's make it interesting by saying we have ice as water, and then we have liquid. The liquid which is surrounding water is not, the liquid which is surrounding this ice is not water. Say it is, for example, it's alcohol. So this consider it as alcohol, not as the one for drinking, but alcohol as a substance, as a hydrocarbon. All right. So let's see what we can write, what equation we can write here. So what equation we can write here is that what will happen, because what you expect to happen is, for example, if this alcohol is, for example, at maybe 25 degrees, and then this ice is at 0 degrees, all right, 0 degrees Celsius, right? We have added these two things. And then this ice block has a certain mass, M. And then also this liquid alcohol has also another mass. Maybe let's call it capital M, a big M. So what will happen is that for the ice, we'll first write the equation to say, since ice is a solid, we expect ice. Okay, in fact, let's consider this ice first. Yeah, just like the way it is at 0 degrees. The equation that we'll write is, we know that the equation for heat, which is required to melt ice, is given by the mass of ice and the heat of fusion for ice. All right, the mass for ice and the heat of fusion for ice. Now, in the equation, we know that energy gained should be equal to the energy lost. So on one side of the equation, we'll write mass, all right, times the heat of fusion of water plus, all right, mass. We expect after all the ice has melted, we expect the heat which will remain, will also try and change the temperature. So we also have mass times the specific heat capacity of water multiplied by the change in temperature. All right, multiplied by the change in temperature. This should be equal to what we have, the liquid, the alcohol liquid. So we write on the other side of the equation, we write the mass of the, in fact, the other mass for the liquid, we are calling it capital M. We write the mass for the liquid, and then we write its specific heat capacity, and we write its change in temperature. This is how we write on the equation. So we know that here on this one side of the equation, we have ice will be gaining what? On one side, we write an equation for what will be gaining energy. Gaining energy. On this other side, we write what? What will be losing energy. Is that okay?
Yes, sir.
So, what will happen is, usually in normal cases, we don't even put this one on the other side. So if we change this one on the other side, we must make sure we put a minus to it, because the actual equation is that we have mass times the heat of fusion for the ice as it will be melting, plus after it has melted, it will start changing its temperature, right? So write the specific capacity times the change in temperature. Then we also add this other mass of the liquid alcohol, its specific capacity and its change in temperature. Everything is supposed to be equal to 0, all right? So if we choose to take this one on the other side, the one that is losing energy, we must make sure we put what? A negative to it. Is that okay?
Yes, sir.
So you will actually see that when we have the session for WASIS. So you have to pay attention to the heat of fusion or the specific heat capacity of what substance, because specific heat capacities are different. For water, it's different. For alcohol, it is different. And for many, many other substances. So you have to be able to take note of that and put that into consideration. But otherwise, if there is no other question, we can call it a day.
Thank you, sir.
Awesome. Have a good day too.